next talk is contributed by Ashland Petroleum. It's a comprehensive approach for routine characterization and ranking of solid acid catalysts. It will be given by Saeed Alerasool. Its co-authors are Pat Doolin and Jim Hoffman.
As refiners at Ashland Petroleum, we have a fluid catalytic converter as one of our primary processes in cracking petroleum. And we would like to optimize our catalyst in order to, our cracking catalyst, in order to be able to minimize undesirable reactions that lead to formation of coke and hydrogen and so forth, and maximize our gasoline yield and so forth. What we try to do then is to characterize the catalyst as best as we can, and one of the primary, of course, the primary driving force behind the catalytic cracking process or reaction are the acid sites. And what we have decided to do more recently is to incorporate acidity determination into our catalyst evaluation program. And to do this, we have tried to make this as routine or as simple as technique as possible, which is almost impossible for acidity, but we have tried our best to simplify it so that we can do it on a routine basis, and at the same time not miss any of the important information about acidity. So that's what I'm going to talk to you about today in the first part of the talk. I'm going to talk about our method. And then I'm going to talk to you about an example of the type of data that we can obtain. And for our example, I've used illuminated YZ light. And I've chosen that because that's essentially what's used in every commercial cracking catalyst. So if you understand the acidity of YZ light and what happens during the deillumination, that is a contribution required for you. But before that, I'd like to just make some general comments about acidity determination of solids in general and how complex it is of a task and what is involved. It is a complex task because unlike liquid, which you can characterize acidity by giving one measure of strength, here it's more complicated because you can have you have acid density, which can be expressed in terms of micromoles of acids per gram or per surface area. You also can have different types of acids, Bronson or Lewis, on the solid, and you can have different distributions of strengths of acid sites because the surface is non-uniform, and it's expected for it to have an uneven distribution. So let's quickly just go through what's out there in terms of approaches. I'm sure you're all familiar with the Hammett indicator method that uses Hammett indicators to probe the strength of the acid site and relies on color changes. And the serious limitations of this method is that it's difficult to detect color changes, especially when the solid is colored itself. And also, these indicator molecules are often too large to penetrate inside the internal core structure of the Z-light. And also they could have steric problems that could interfere with the determination. We're normally far away from reaction conditions, and we definitely cannot discriminate between Lewis and Bronson acidity when we use Hammett indicators. The other general category of approaches deal with using gaseous probe molecules, and that's a very popular approach, and thermogravimetry has been tried quite extensively. Microcalorimetry has been used more recently by people like Jim Domestic to generate a very detailed profile of the strength distribution based on heat of absorption following dosing the surface with pyridine, for example. And obviously infrared spectroscopy, which is able to discriminate for us between Bronson and Lewis acidity. There's a wide body of probe reactions that have been used, and among those, dehydration of methanol has been used for weak acidity, cumin cracking has been used for moderately strong acidity, hexane cracking used for strong acidity, and again, more recently, Gordy and co-workers have tried to use isopropyl amine cracking as a probe for strong Bronson acidity. So, having examined these approaches, of course, there's more sophisticated methods out there like XPS and solid-state NMR, in addition to those, but within the realm of our capabilities, we decided to come up with a multi-technique method, and that, in our view, was the only way to go because there is no single approach or technique that could give us all the information. Our technique uses pyridine and uses thermogravimetric analysis to determine the total acidity or acid density. And the way we do this is we, after calcining the sample at 400 degrees C, we run a nitrogen pyridine mixture over the catalyst, and when it levels off and there's no more uptake, we stop and we calculate the total acidity. And to make sure that we eliminate diffusion problems and so forth, this runs for at least 7 hours normally to reach a complete plateau. And if we want to obtain a strength profile distribution, we go through stepwise desorption and calculate the amount that desorbs off in different increments of temperature. We do the acid type by diffuse reflectance infrared spectroscopy, and we've heard a lot about that this morning, and pleasant surprise. And we've chosen that as a method of choice too for determining the type. And we have chosen hexane cracking as a way of looking at strength of strong acid site. And again, we measure here the activity, the initial activity of the catalyst at 400 degrees C, very early in the onset, normally at 5 minutes, and we calculate activities at that point. There are several advantages to these combination methods. First of all, the choice of pyridine, I think, is a good choice because it realistically measures the number of catalytically important sites. I'd like to go into more detail with regards to that, to justify that. And what we have done here is we've calculated the total number of exchange sites on the ZSM5 sample and hydrogen Y, and then we measured the total acidity with pyridine. And you can see that with DSM5, these two values agree quite well with each other, but there's a wide difference between the two for hydrogen Y. And why that is due to the structure differences between these catalysts, these two zeolites. And in the case of Y zeolites, you have the sololite cages where the openings are not big enough for pyridine to get in, and therefore you miss the sites which are associated with sololite cages, and as a result, you don't measure them. But if pyridine cannot get into those or approach those sites, neither can any of hydrocarbons of interest to us. We really, therefore, do not want to measure those sites. And unlike CSM5, where you have straight zigzag type channels with interconnected pores, which they all have openings that are large enough for pyridine to access, here, therefore, we get better agreement. But here, we get a disagreement, and that's to our advantage because we would like to miss the sites that are not accessible to our hydrocarbon. But we haven't done measurements with ammonia. We have compared ammonia measurements in the literature and some cross-laboratory measurements that we've done, and ammonia comes much closer to the theoretical value, and in our view that is a disadvantage because ammonia can measure sites that are not important to us. Now going back to this slide again, we use TGA because it's easy, accurate, and fully automated to use. Drifts, I don't need to go through the advantages of it again, but one clear advantage for us is that we don't need to make pellets for drifts. The other one is that we are normally looking at lower wave number region where drifts gives us better signal. And hexane cracking is a good probe for our strong acidity because we are essentially dealing with cracking catalysts that are in that region of strength. So having gone through the description of our method in some detail, let us go to the second part, which deals with the illuminated zeolite. And what we wanted to do is we wanted to investigate, first of all, the dependence of acidity on the cell side. We wanted to look at differences between chemical and steam deillumination. And we wanted to see, as you deilluminate, what changes take place in the nature of the acid sites. And very importantly, we wanted to look at the role of extra framework aluminum, which is generated. The samples that we prepared, we started always with commercial Davison sodium Y, which we exchanged the sodium out of it. And it had a 24.77 angstrom unit cell, as measured by XRD in our laboratories. And the chemical deillumination we did by very slow treatment of the zeolite with ammonium hexachlorosilicate at a very slow rate, not exceeding 2 milliliters of the compound per hour, because if you speed up if the treatment is too fast, you collapse the structure. And then washing and drying, which is repeat. The steam deillumination was then very standard, shallow bed type, and we did for 1 hour steamings at 260 degrees, 400, and all the way ranging to 565 degrees C, generating the whole range of illuminated zeolite. Let's look at some properties of the materials that we generated. The top part of this table lists the chemically deilluminated samples. We have fewer of those because we started to lose crystallinity here, and since we wanted to be able to look at extra framework aluminum, the absence in one case and the presence in the other case, we stopped here. And then a series of steam deilluminated ones, the range of unit cell went all the way to 24.35. But we do have an overlap region where we can make good comparisons. And the extra framework aluminum we calculated from the equation proposed by Zone and co-workers. So it's not by solid state NMR, so it's not a direct measurement, but it is a calculated measurement. But you do see that the absence of extra framework aluminum in the first set and the presence and the increase as you go to more severe steaming conditions. So now let's look at what we get in terms of acidity of these materials. Well, before that, let's look at how these materials vary in terms of their silica alumina. For chemically deilluminated materials, there's a very good agreement between what you calculate in the framework and what you measure in the bulk by XRF. So this is another indication of the absence of extra framework aluminum in chemically deilluminated case. Here, you see the wide difference here. between these two sets of samples. As you go to more severe deillumination, this is what happens to the framework, and this is what happens to the bulk, which is practically nothing, it's constant. So this should be interesting, or that we should be able to make good comparisons in terms of the role of extra framework aluminum from these samples. Now, this is the effect of deillumination on total acidity. And what we have here is the chemically deilluminated ones, and the steamed ones are with the dotted line. And the total acidity is expressed in terms of micromoles per gram. What we see here is consistently the chemically deilluminated ones have a higher number of total acid sites. That's not surprising. That's a combination of three factors. First of all, in the steamed one, you're collapsing part of the structure, so you're losing the site. Secondly, in the chemically illuminated case, you have an enrichment of sites on the outer surface of the crystallite, so you have more acid sites on this, contributing to this difference. Now, in terms of hexane cracking activity, we see the opposite. The steamed ones, as you go further on in steaming, the cracking activity increases substantially, and at this constant unit cell, at the same unit cell size, that of steam deilluminated one is much higher than the chemically deilluminated sample. And since we were able to go to smaller unit cell size here, we went through a maximum for steam deilluminated ones, and that is maximum at 24.44 almost, which is where all the aluminum sites or the acid sites are isolated at that point. So you have, beyond that, the acid strength should remain constant, and you just get rid of the sites that you have, so activity goes down. Now, it was obvious from the previous slide that the differences between these two were not due to the total acidity. So if we thought that if this is directly related to strength, we could come up with a strength index from these data, combining total acidity with hexane cracking activity data. So we made a bold attempt in trying to combine these two sets of data, and we normalize N-hexane cracking activity values with respect to total acidity obtained from pyridine, and the value you get is like a turnover frequency type value, which we think is directly related to strength. And it provides an average measure of acid strength in strong solid acid. And we went to the literature, and the values that we are getting in this column are very comparable to the data that exists, particularly by Keith Hall, where silica alumina and hydrogen wire gives us the lowest strength, and so does and they do have the lowest Hammett numbers. But when you go to ultra-stable Y, which really is a severely steamed zeolite, you get the highest acid strength, and then for mortonites and DSM-5, you even get stronger sites than USY. So that was encouraging. And we also used our strength index to see how we can distinguish between various types of modifications on zeolite. We added to the previous series a series of cerium Y, and the cerium Y series, they lie right in between the chemically deilluminated samples and steamed samples. And from these data, you can conclude that, as far as we have found out, the best way to achieve the highest strength in a Y-type zeolite is to steam it than doing anything else. And going back to our two sets, we see that the strength index is much higher for steam deilluminated samples than it is for chemically deilluminated samples. And it looks like we don't have enough materials out there to say with confidence, but it looks like this does level off. Hopefully it will. And what we think here is that's the same point as that maximum that I was talking to you about, 24.44, beyond which the strength should remain constant. The primary difference between these two materials are the extra framework aluminum. So what we wanted to find out is how do these materials or how do these species actually contribute to the higher strength, and that's where we looked at the infrared of these materials. And this is all drift data, so this should really be drift absorbers. I have here the spectrum of a number of our samples. This is typically where you see on a pyridine poison sample. This is at 150 degrees C. You see a peak at around 1540, the band corresponding to a Bronsted type of acidity, which is like pyridinium ion, and the band representative of Lewis acidity at 1450. And what you see on these samples is that hydrogen white doesn't seem to have any Lewis acidity in this region. It's all Bronsted. And for chemically illuminated samples, also you don't see any Lewis acidity. But for these two materials, which are really the same unit cell, the steam sample has considerably more Lewis, or has a significant amount of Lewis acidity, where the chemically illuminated one doesn't. And this we associate directly with the extra framework aluminum. And the question is, how are those extra framework aluminums, are they directly responsible for the higher cracking of these materials? To partially answer this question, shed some light on it, we did desorbed the pyridine poison sample at 350 degrees C, which the pyridine which is left at this temperature corresponds to stronger acid sites. And we plotted Lewis over Bronsted ratio for these different materials, and at 150, which corresponds to all the weak and strong acid sites, you see a definite correlation between, as you illuminate these materials and you go through more severe steaming, the Lewis to Bronsted ratio goes up. But when you go to 350, there is really no significant amount of Lewis acidity left. So this points, in our opinion, to an inductive type of effect, that Lewis sites are inducing strength into their neighboring Bronsted sites rather than directly participating in the reaction itself. So with that, I'd like to conclude. We found that deillumination leads to a decrease in total acidity, which is not surprising. A mild increase in acid strength is achieved by chemical deillumination, which is really a direct result of isolating those aluminum tetrahedral sites. But you really increase the strength when you introduce extra framework aluminum, and those are associated with Lewis acidity. The acid strength index that we calculated, we found that it is a good measure of acid strength index and compares well with candidate pairs, at least for the range of materials that we tested. And combination of pyridine thermogravimetry and infrared spectroscopy with N-hexane cracking can be effectively used to determine density, type, and strength of solid acids, which in our opinion are really the three important aspects of solid acidity. And although the individual techniques are not unique, the multi-technique approach, in our opinion, is somewhat novel. Thank you, and I'd like to acknowledge Ashton and Oil for allowing me to present this paper.
Any questions? Bert?
What temperature did you do the hexane cracking?
400.
And you didn't make the acidity measurements at 400, but 350 is similar enough?
Pardon me?
The acidity measurements you made at 350, did you also make them at 400 where you took the ratio of Lewis to bronze?
Yeah, we did make acidity measurements, not at 400, but at 350. But the hexane activity values we obtained were done at 400 degrees C. We used the pyridine measurements at 150 as a measure of total acidity, and there we assumed that for the range of YZ lights that we were working with, the acid distribution was narrow enough that we could use the total acidity as measured by pyridine as a way of normalizing.
Do you have a correlation between Bronsted acidity and hexane cracking activity?
We do, but we're not ready to talk about that yet. We don't have enough data, but I have strong feelings that there's a direct correlation between Bronsted Pardon me?
For a given sample, is there any complete distribution of acid size? Say it looks as if you are comparing the different samples. For a given sample, is there any that will correlate in that? Because strong acid sites are to be poisoned by the cracking by the coke deposit.
Well, that's why we measure activity right at the onset of the reaction, and that's as early as we can make the measurements. We take them, which is 5 minutes into the reaction. We don't seem to get more reliable measurements to try to get it earlier on than 5 minutes.
Because from my experience, it looks, if you have the acid site distribution like weak, medium, and strong acid sites, no doubt they will catalyze the reaction very fast.
Right.
But they are the one which will be poisoned fast.
But how fast do they get poisoned? That's the question.
Okay. The medium acid sites might play an important role when you increase the temperature of the reaction. That is, as the catalyst ages, you will increase the reaction temperature. And that time, medium sites are the ones which are going to contribute a lot. Therefore, if you have the complete distribution of sites for a given sample, then you can understand better the catalyst performance.
Well, we do for every sample. I didn't show that data here. What we routinely do, we generate a strength profile for different samples. And what we do, if you're just wanting a crude measure, we go to 350 and calculate the total uptake at 350. And that's, we get a kind of distribution that way. And we do see a correlation between percentage strong and the hexane cracking data. In other words, as you go to a smaller unit cell, the percentage of strong acidity goes up based on our TGA measurement.
Thank you, Saeed. Our last